The guided examples at the end of this video will require you to know how to use the trig ratios, including the buttons on your calculator, and to calculate unknown sides and angles in right triangles. You also need to be familiar with all three methods for giving compass directions, using either the cardinal points, a compass bearing, or a true bearing. If not, I recommend you watch video 7a in this series, Understanding Bearings. Keep in mind also that real-life problems, especially over large distances, would need to take into account the curvature of the Earth as well, using arcs and spherical triangles rather than straight lines and flat, plane shapes. This is a whole separate branch of trigonometry, unsurprisingly known as spherical trigonometry. In example 1, a ship travels 14.2 kilometers northeast. How far north is it from its starting point? Starting with the cardinal points, as already demonstrated, we can add in the northeast direction, halfway between north and east. We are told the distance travelled along this direction was 14.2 kilometers, and we know that the northeast line makes an angle of 45 degrees with the north line, and also with the east line. So we could use this triangle or this one. In either case, x shows us the northerly component we wish to calculate. Labelling our sides and using SOHCAHTOA, we see that the sine ratio is required. Opposite over hypotenuse is sine, so x over 14.2 must equal the sine of 45 degrees. 14.2 multiplied by the sine of 45 degrees gives us this answer on our calculator, telling us the ship is 10.0 kilometers north of its starting point. If your calculator doesn't give you the correct answer, then check that it is correctly set to degrees. Alternatively, this question can actually be solved without using trigonometry, using Pythagoras' theorem instead. Since this angle is 45 degrees, then so is the remaining one. The two angles must add to 90 degrees, or you could subtract 90 and 45 from 180. Two equal angles means we have an isosceles triangle, with both these sides equal to the as yet unknown value of x. Substituting into Pythagoras' theorem gives us this, so that 2x squared is 201.64. Halving this is 100.82, and finding the square root reveals x is 10.0, correct to one decimal place, as before. In example 2, this time the ship sails south-southwest, reaching a point that is 10.7 kilometers south of its starting point. We are told this southerly component is 10.7 kilometers. We want to know the actual distance sailed, so we mark our pronumeral x here. Halving our right angle twice, we find that this angle is 22.5 degrees, although you might simply remember that it is so. We could use this triangle or this one instead. Labelling the sides, we find that the cosine ratio is required. Transcribing the information carefully reveals that x is on the denominator this time. Remembering our handy shortcut, as we discussed in earlier videos, we end up with 10.7 divided by cos of 22.5 degrees, giving us 11.6 kilometers, correct to one decimal place. Using the other triangle requires the sine ratio instead, leading to 10.7 divided by sine of 67.5, naturally still giving us 11.6 kilometers as before. You might like to try example 3 before I work through the solution. We should first realize that 214 degrees is more than 180, so the bearing is past south, but before west, since it is also less than 270 degrees. Subtracting 180 from 214 reveals that it is an extra 34 degrees past south. Camp A is our starting point, and Camp B is the end point, which is 750 meters away. Here is the most obvious right triangle to use. Following our usual process, we find that x over 750 must equal cos of 34 degrees. Thus, x is 750 multiplied by cos 34, giving us 622 metres when rounded to the nearest metre. 620 metres to the nearest 10 metres would also be acceptable, since we can't tell whether the 750 metres was recorded to the nearest metre or to the nearest 10 metres. In this final example, we are asked to determine the bearing, given relevant information. Similar to coordinates, we are told the location of campsite B compared to campsite A being 250 metres west and 300 metres north. We need to find the bearing of campsite B from A, which is this angle all the way around up to here, labelled theta. We should immediately notice that it will be more than 270 degrees. We need a right-angled triangle that will help us find this bearing. Calculating this angle, labelled beta, is one way I can achieve this. Following our reliable process, we find that the tan ratio for this angle must equal 300 over 250. The inverse tan function, pressing shift then tan, will reveal the size of the angle. Rounding to the nearest degree is sufficient unless told otherwise, so beta is 50 degrees. Now we can easily find the value of theta by adding the extra 270 degrees, revealing that the bearing of campsite B from A must be 320 degrees. Alternatively, we could have used this triangle instead, meaning we would calculate this angle as beta. Following the same process, we still use the tangent ratio, but its value is the reciprocal of the previous example, being 250 over 300 instead. This leads to theta being equal to 40 degrees instead of 50 degrees. Our required bearing, theta, will be 40 degrees less than a full revolution, so subtracting from 360, we find the bearing again to be 320 degrees.